Hey guys! My name is Earl Royce Hugo and today I'm going to teach you the basics of graph coloring. First and most important of all, this is not what I'm referring to. Nope. In discrete structures, a graph is a mathematical model that represents relationships between objects. These objects are shown as points called vertices. And the relationship between two objects is represented as a line segment or an arc, called an edge. Two related vertices, or vertices connected by an edge, are called adjacent vertices. In the example shown, vertex B is adjacent to A and C, while vertex D is adjacent to C, E, and F, and so on for the other vertices. Graph theory has multiple applications, including graph matching, shortest path, and minimum spanning tree. For this video, we are going to look at graph coloring, plus some bonus material if you stick around. Graph coloring is the assignment of colors to the vertices so that no two adjacent vertices have the same color. Here are some examples. The color referred to here may be actual colors as shown, but they can be any distinguishable marker, like letters or numbers. If the graph can be properly colored by n number of colors, then the graph is said to be n-colorable. In the examples below, we can conclude that the graph to the left is 3-colorable, and the graph to the right is 4-colorable. Looking at this 4 cycle, we can see that we can in fact achieve proper vertex coloring by simply using different colors for the different vertices, but that might not have as much real-life applications. We can show that this graph is actually also 3-colorable and even 2-colorable. The beauty of graph coloring comes with a property called the chromatic number, represented by chi of graph G, which is the minimum number of colors for which a graph is properly colorable. If the chromatic number is a certain number k, then the graph is said to be k-chromatic. Going back to our graphs, the graph to the left is 3-chromatic, and the one to the right is 2-chromatic. You're probably thinking, does this actually solve anything, or is it just an exercise to keep kids entertained? Well, there are in fact various uses for graph coloring, including scheduling, map coloring, and even solving Sudoku. In computing, graph coloring also has practical applications. For example, when designing IT infrastructure. Imagine that you are an architect working on a project with limited budget. Your customers' applications require 5 resource-intensive jobs to run regularly, and these jobs cannot be running at the same time simultaneously. Given the following schedules for jobs A to E, you might be tempted to commission 5 separate servers. But is that cost efficient? We can solve the minimum number of servers using, you guessed it, graph coloring. To start, we can represent any job schedule as a vertex, and any conflicting schedule can be connected by an edge. Coloring these using numbers, we have 1 for A, 2 for B since it's adjacent to A and cannot have the same color, 1 for C, 2 for D, and 3 for E. Of course, in real-life design, there are other considerations like total number of users, capacity planning, and redundancy. But in terms of the concurrency of the resource-intensive jobs, the minimum number of servers is the chromatic number, which is 3. That's all for now for graph coloring. Thank you for watching. I hope you learned something new. But wait a minute, since I still have time on this video, let me tell you a little something about Rubik's Cube. Did you know that it's theoretically possible to represent the solution to a Rubik's Cube using graph theory? Imagine a graph with vertices that represent each configuration of a 3x3x3 Rubik's Cube. Each vertex will be connected or related to any other configuration that is one move away from the current configuration. An efficient solution, therefore, would be the shortest path or the minimum number of moves from the scrambled position to the solved position. Note, however, that there are about 43 quintillion such positions, so it might be faster if we just Google a solution. How did we get 43 quintillion? Now that's a lesson for another day.